Hello, and thank you for your interest in our Tech Talk presentation. Materials Research and Design out of Wayne, Pennsylvania, abbreviated here on as MRD, is very excited to share with you our current progress and plans on developing an innovative deep learning-based software for composite material analysis. This software program was created in response to Navy topic N68335-23-C-0609 for the Office of Naval Research. A little bit of background on MR&D, we provide specialized research, analysis, and design services to the advanced materials community, focusing on composite and ceramic materials for aerospace applications. With 20 experienced engineers all holding advanced degrees and a multitude of computational design tools, MR&D is well equipped to conduct advanced structural and thermal analysis, material design, test design, post-test data correlation, and guidance for manufacturing. You can see some examples of our detailed computational models in the animations on screen. Our company also has hundreds of partners, including those in the government, aerospace, defense, manufacturing, and commercial sectors, some of which are also listed on the slide. Now, material that is often used by our partners and the broader defense, aerospace, and commercial industries is a woven fiber composite, made up of two main constituents. First is a woven fiber fabric like the one shown in the top right image, and some sort of matrix material, either a ceramic or polymer, to adhere the woven layers together and thus formulate a complex structure of fiber tows, which provides an effective combination of mechanical and thermal resilience. Despite the growing usage of these composite materials, there are still many uncertainties that arise during the manufacturing process, often resulting in unintended quality defects that can skew the material's key performance characteristics, such as stiffness and strength. Such defects present from manufacturing and the comprehensive analysis that's required to understand the as-manufactured part drastically increases the time and cost of a project. In most instances, this comes in the form of long-term structural testing to certify a part's usage and/or increase fabrication costs to manufacture over conservative designs. This is of great concern to the Navy, which uses woven composite parts in a wide array of vehicles that require the sort of mechanical and thermal strength only these materials can provide. The Navy and its contractors need a computational tool that can be efficiently implemented to evaluate the quality and mechanical properties of as-manufactured parts. Such a tool would help reduce the time and cost required for mechanical testing and certification by quickly evaluating overall quality through measures like stiffness, strength, and constituent material volume fractions. Additionally, these results could be used to optimize the part's design and/or accompanying manufacturing processes. MR&D is developing a comprehensive software tool to cater to the Navy's and the broader industry's needs. This software tool works to automatically analyze the quality of a part directly from a computed tomography or CT scan. Using trends in fiber architecture, material phases, and flaws or voids that can be observed from the part CT scan, the software predicts material volume fractions as well as mechanical properties to be used as a preliminary quality assessment or as an input for more detailed computational models. To facilitate widespread accessibility, the software is a plugin built for the open-source image processing software known as ImageJ. Under the hood, this plugin is an artificial intelligence tool, allowing for the construction of a convolutional neural network that needs only a small amount of user input to efficiently extrapolate fiber architecture trends to large volumes of CT data. As shown in the images of the graphical user interface on the right, there are multiple modules of the plugin to facilitate simple and quick analysis. The first one is called the Mask module, shown in the top right image, where the user can use simple painting and grayscale thresholding tools to specify distinct material phases for a small subset of CT data. For example, out of a large CT data set of 1,000 images that they wish to analyze, the user could pick out 10 to 20 distinct images to manually specify the material phases to train the software. After specifying this data for training, the user can then train the network in the module shown in the bottom right. Here, the user will define various input parameters and the data that they would like to construct the neural network around, and once the training begins, the software will generate a line plot depicting the expected segmentation accuracy of the algorithm they're creating. After training, the user will run the algorithm in the module depicted in the top right. This is the step in the analysis where the trained deep learning network is used to segment a much larger volume of CT data while providing the user with previews of each segmented material phase as the network is applied. Once this segmentation is complete and the user has a good idea of the results, they can input constituent material properties to each phase of the segmented data and predict mechanical properties using the finite element analysis or FEA module depicted in the bottom right image. With each material phase defined, the software will take a few more additional input parameters and impart periodic displacements in each direction to calculate the orthotropic mechanical properties of the composite material. The final module of the software is an integration with the open source woven composite modeling software called TextGen. To convert the segmented image volume generated by the deep learning network to a solid geometry, the user will trace distinct cross sections for each visible fiber toe to define its path in a specified direction. The cross-sectional shapes and the locations of each fiber toe within the image volume's dimensions are then saved to a script that can be readily opened in TextGen, either for direct conversion to a solid part geometry or for manipulation for further FEA analysis in other software. MR&D has made great strides to develop the software into what it is today. We have created and stress tested multiple builds of the software over the course of the Navy Phase 2 effort. For our software to reliably approach a technological readiness level of 4 for implementation into assembly line or design environments, MR&D has outlined a few goals and milestones we'd like to achieve. The first is to construct pre-trained neural networks to package with the software to eliminate the need for the user to have to create their own and to be able to generate quick segmentation results reliably. Additionally, we'd like to optimize the back-end code to reduce runtimes for image segmentation and property calculations, and we'd also like to conduct continual accuracy studies to ensure the software matches or exceeds the performance of existing commercial solutions. Each of these tasks will cater to the 3 distinct milestones shown in the table at the bottom right. Many of the software's advantages and benefits stem from the individual modules that we discussed previously. The first primary feature is the Training Data Mask Creator, which allows a user to create their own specific set of training images in the construction of their custom segmentation algorithm. While using a pre-trained network packaged with the software will be an option we're working on developing, the benefit with this feature is to allow the user total control over the construction of the algorithm that they're working on and the results that the algorithm will generate. The next key feature is the implementation of the convolutional neural network architecture and the pre-trained networks the software will come packaged with. The main advantage of an advanced artificial intelligence algorithm implemented via a convolutional neural network in our software is its efficiency and accuracy in segmenting large datasets while requiring very minimal user input. This leads to reduced CT data processing times compared to other methods, while still giving usable material quality assessments. Next is the FEA model solver, which takes minimal input from the user to measure the material's structural characteristics. The benefit of this feature is that it is purely computational, enabling maximum assembly line efficiency and requiring no physical testing to get a reasonable prediction of how the material will perform. The final main feature is the software's integration with TextGen. Pairing it with specialized software is advantageous for providing the user with more ways to process their CT data and manipulate the geometry if they wish to. The benefit of this is that it allows the user to easily modify their part to explore design or manufacturing process changes. This feeds into the last defining feature of our tool, which is that it serves as a one-stop shop for most CT data processing functions a user would want. Such software is implemented over top of existing free tools and can be run on a variety of different computers with minimal user training. Given these defining features and the progress made towards developing each one, MR&D believes that the software will achieve a TRL of 4 in a timely manner such that transition can happen soon after the conclusion of the Phase 2 effort. MR&D's continual software development will advance the final product to the point that it can be reliably used by the Navy and its contractors in the analysis of woven composite parts with carbon matrix composites, polymer matrix composites, and the like. Although the goal of the Phase 2 effort is to use this tool in the analysis of airframe components specifically, MR&D believes this software will be very useful elsewhere for analyzing parts that use woven composites. Not only this, but MR&D believes this software can be used in a multitude of other government, aerospace, defense, and commercial applications. MR&D sees promise in licensing access to the software to various industries or companies that utilize composite parts and need easy-to-use and in-depth analysis tools for these advanced materials. While commercial software solutions offer similar features for segmenting images with neural networks, MR&D believes they can close a gap in the market by introducing a specialized suite of tools to easily process segmented CT data into usable FEA and geometrical models, which has been a long-standing issue in the development of digital twin models. MR&D is confident that this value proposition is favorable when reaching out to other potential government, aerospace, defense, and commercial partners, many of which MR&D has already formed relationships with. MR&D believes that the need for such a comprehensive tool is bound to increase as the popularity of woven composite materials also increases, so the outlook on the development and transition of our software is very positive. This will be facilitated by MR&D's long-standing industry connections and the exercise of our technical prowess to ensure the seamless transition of our software to the wider market. If you would like to find out more about our software, or you would like to discuss technological solutions MR&D may be able to provide you, you can use the listed means of contact to reach out to us at any time, and we will get back to you as soon as possible. We will also be attending the 2025 Sea Airspace Convention if you would like to connect with us in person at the Navy STP program booth as well. In the meantime, thank you so much for your time and your interest in our Tech Talk presentation.